Okay, this is Mr. Thornton speaking to you from the distant past before Thanksgiving. Got a little jazz on, and we're going to do this last lesson of Chapter 7, Continuous Growth Applications. So, continuously compounded interest. Continuous compounding is when the number of times the interest is compounded increases to infinity. So we're going to do show you why this is what it is before we get to the formula itself. Start with the formula for compound interest. We have here A of t is equal to P times 1 plus R over N to the NT power, which we have in the last lesson. And we're going to let M equal N over R. So I can see that that is exactly the reciprocal of R over N. So I can write the principal times 1 plus the reciprocal of M, 1 over M. Now, if I take M is equal to N over R, and I multiply both sides by R, I get MR equals N. So I'm going to replace N here with MR, and then I still have T. So I have MRT, Mr. T actually. Okay, so A of t is equal to P times 1 plus 1 over M to the MRT power. So doing a little regrouping here, I can say that A of t equals P times 1 plus 1 over M to the M power. So I'm just kind of moving the M out to the RT power. So if I take this and I say let M go to infinity, M approach infinity, then this piece in here, this 1 plus 1 over M to the M power, that is the precise definition of E. And what I end up with is P times E to the RT power. That is our continuously compounded interest formula, which is restated here at the bottom of the page. So push up a little bit. Continuously compounded interest, A of t, is equal to PERT. P times E to the RT power. A of t, again, is amount at time t. P is still your principal, your initial investment. R is your interest rate, which is now in the exponent, different from our original. And then T is still in years. So on the back now, number 1 says $4,000 is invested at an annual rate of 6% compounded continuously. Write a formula for the amount in the account after T years. So we're going to use the PERT formula. A of t is equal to our principal. What we start with is $4,000 times E. Remember, E is approximately 2.718, whatever it is. 4,000 times E to the R. R, my interest rate, is 0.06 T power. So 4,000 times E to the 0.06 T power. How much will be in the account after 5 years? Well, let's bring in our handy little calculator here. And we're going to say 4,000 times E. To get E, I'm going to do second ln. So my second button is the blue button, and then ln is right below log, and it will put a little E with it. Automatically puts an exponent on the E, which we're going to put in for the exponent. We're going to put in 0.06 times 5. So 4,000 times E to the 0.06 times 5 power, and I get $53.99 and 44 cents. $5,399 and 44 cents. So A of 5, let me just write this down real quick. A of 5 equals 4,000 E to the 0.06 times 5. Compare this amount to the amount found on example 4 of N7-7. We had 53.8742 when we did quarterly, 53.9540 monthly, and a little bit more, 53.9944 if we compound continuously. Notice, the more often we compound, the greater our amount is, the more interest we will be earning. It's a pretty good jump up from quarterly to monthly. Not quite as big a jump up from monthly to continuously. About, and in between here, if we did daily, it would fit in between monthly and continuously. So, continuous growth or decay here. Similarly, a quantity that grows continuously can be written with the base B is equal to E to the K power. And so we have this formula: a of t equals a sub 0 e to the kt power. A of t again, amount at any time t, a of 0, amount at time 0 or initial amount. K is going to be our rate, the rate of continuous growth or decay. And if it's positive, we get growth. If we get a negative K, that is going to be a decay situation. And then T is going to be your time, and depending on the situation, that might be years, it might be days, it might be minutes. You just never know. All right, last example, number 2. The approximate number of fruit flies in an experimental population after T hours is A of T is equal to 20 times E to the 0.03 T. Notice our K value is positive, so it is going to be growth here. We have growth in the number of fruit flies. So what's the initial amount? Remember that A sub 0, which is 20 here, is our initial amount. We also get that if we put in 0 for T. 0.03 times 0 is 0, e to the 0 is 1, 20 times 1 is equal to 20. What's the population after 24 hours? Well, we're going to say A of 20 equals 20 times e to the 0.03 times 24. So 20 times, I'm going to hit second, ln, to get that e to the 0.03 times 24 hours. And we get 41.088. 089 actually. But we're going to round that, since we're talking about fruit flies, I'm going to round that to 41. It's approximately, I got 41.089. So I'm going to say 41 fruit flies here. Okay, so we're going to solve part D by graphing. How long will it take for the population to reach 100 flies? So I'm going to put in my equation, y1 on the graphing calculator, 20 times e to the 0.03x instead of t here. I'm going to use x. For my window, I know that it's going to double, approximately double in the first 24 hours. If it doubles again in the next 24 hours, that'll put me 82. So I think that I'm going to say within 100 hours, I'm pretty sure I'm going to hit 120, I'm going to hit 100 flies. So I'm going to say 0 to 100 hours here. For my y values, I'm putting in 0. I know I need up to 100, but I'm going to put 125 just to give me a little wiggle room above. And when I graph that, here's what I have. Okay, so here's my exponential equation with the e. For my y2 value, I'm going to put 100. Oops, excuse me. That was 20. y2, I'm going to put 100. So here's my original function, 20e to the 0.03x. Here's my 100. There we go. And I'm going to find that point of intersection. Second trace 5. I'm already pretty close to it. I'm press enter for guess 1. Second curve, guess. There we go. And I got 53.648. 53.648 hours. 53.648 hours when I graphed. My y1, excuse me there, y1 was 20e to the 0.03t. Actually, I used x there. And my y2 was 100. And I found the intersection of those two. 53.648 hours, we should have 100 flies. Finally, you have a summary here. I will give you these formulas when we take a test later this week. I will give you these 5 formulas for our growth and decay problems, for all the application problems. All right. That takes us to the end of this lesson, and I've got a little treat for you here. Pull this down so you can see. Here is a deep thought by Jack Handey. This used to be on writer for Saturday Night Live. I think he's very funny. So here is today's deep thought by Jack Handey. Whenever I see an old lady slip and fall on a wet sidewalk, my first instinct is to laugh. But then I think, what if I was an ant and she fell on me? Then it wouldn't seem quite so funny. You're welcome.